So then I want to start the presentation. So the title of the presentation is Flexible eFPGA-based demonstration platform for die-to-die interface testing. So again, it's a common presentation between Fraunhofer and Achronix. So short agenda for the talk today. We want to show we have the introduction, we have the use case that we have in mind from Fraunhofer side. We have the overview about the platform, the description of the die-to-die interface we use. Then we go to the introduction of this eFPGA technology, why eFPGA technology is ideal for the chiplets, and then we have the combined solution and the summary. A short introduction regarding Fraunhofer. So Fraunhofer is a German research institute, an applied research institute. We are a research partner here in Europe, in Germany, in Europe, for different types of advanced packaging. So we work on this chiplet integration. Here we work together with partners from system level up to the physical implementation level. So we start with system concepts, power delivery concepts. We work on the heat removal and the die-to-die interface development and on system implementation. So our work is not only focused on chiplet integration, we also work on different types of advanced packaging like antenna in package or die stacking for real 3D stacking.
Thank you. So yes, Achronix is a manufacturer of high-end FPGAs. We have what we call our Speedster family, in this case the Speedster7t, and we also provide IP. We also are an IP provider for FPGA technology, what we call embedded FPGA technology, that is used by our customers, in the case of Fraunhofer, to build their own devices with the FPGA technology integrated inside of the die. And then we also provide PCIe evaluation cards with our FPGAs on them that can be used for doing product development or even productize the cards themselves. We also have a tool suite that we call ACE that does synthesis verification, timing programming, and debug. And if you want to learn more about Achronix, we are going to be down at booth 306 starting tomorrow. Back over to Andy.
Okay, then we want to show a little bit use cases that we have in mind, especially also with this, if we use the eFPGA, how such chiplets can look like. So one big, we see a lot of requirements or a lot of, we see that certain companies want to go to chiplet, especially in this measurement equipment. So that's not a big market, it's more a niche market, but here we really have the needs for chiplet integration in the future, because we have here high-speed data acquisitions in the range of gigabit or terabits in a very small number of channels. That means we have a small interface with huge numbers of data that must be processed. The problem here, or the reason here to go to chiplets is single chips, single SoCs can't fulfill the requirements anymore at these systems. So we need the analog to digital converters, and for these high data rates, they need very specific technologies, chip technologies like CK or indium phosphide. And on the other side, we need for the processing, we need digital pre-processing, and we also need digital processing, and both must be done in very advanced nodes, so 16 nanometer, 7 nanometer, 5 nanometer. So there's really no chance to combine all these things together. And compared to older approaches where the NDC and the digital part can be combined together on the PCB, that's no longer possible because of these huge data rates. So that's really a use case where we see the needs for heterogeneous integration with chiplets, where it really makes sense to go forward. The second one is in the field of automotive. So here we have also the high-speed data acquisition in the range of gigabit or terabits per second. But here it's a little bit different, because here we have more number of channels, we have more lidars, radars, cameras in the future. But also here we have then similar requirements. On the one side, we have the sensors, we have digital processings in different ways with CPUs, DSPs, and so on. And also here, often an eFPGA or an FPGA is needed because during the lifetime of a car, a certain reconfiguration must be done, adaptation to on the interface side and so on. And here it's more the way that we want to go to use chiplets we want to use this idea of building blocks, to use building blocks to be flexible, to build flexible configurations for different types of cars. So you have we have a set of predefined components, and you build different configurations for different types of cars. So from the architectural side, we have certain things in mind. It's a little bit different to that what is seen in some other presentations. So for this specific applications, what we have in mind, it looks like we have the block diagrams looks like that, or similar to that what we show here. So we have architectures where we have a general hub, and we process then the data from the sensor to the FPGA and back and to the DSPs. But then the hub in the middle has to process a huge amount of data. And on the other side, there are maybe architectures, better fitting architectures available in the future. This is what we are also looking for, and what we are researching here now. What is the best architecture for such application? And here you see then that you need then maybe also the chiplet interfaces on the FPGA on different sides, because it's not that central hub in the middle, and that means, again, we have to do here this system exploration. We have to look at the system exploration. What are the right configurations to build then also the right chiplets themselves with the interface on the right sides. And here we see that the right architecture much better fits to these data streams, how the data streams through the application. So it goes directly to the eFPGAs. On the beginning, we have the pre-processing. And it's not the central element is not necessary, where we have on the end maybe blockages because of this, because of that everything, all the data must go to one central element. So this is again something that we see that it must be explored much more in the future. What are the right chiplet architectures for specific applications? So then I want to hand over again. Oh no, sorry, one more slide. Which interface we are using here? So we are working on a bunch of wire and UCIe. Both is what we are using. We have implementation in different technologies available, up to 16 gigabit per second option, and for that again we have implementation available here and can be used for this project.
So, thank you, Andy, for talking about the use cases that Fraunhofer is exploring using either UCIe, bunch of wires, different architectures. What Achronix is, we've provided Fraunhofer with an embedded FPGA technology, but I just want to baseline everybody here on what FPGAs are. I'm not sure if everybody understands what the FPGAs are, but it's an integrated circuit that can be reprogrammed after manufacturing, meaning in the field. That's what's field programmable. It typically has a structure that are what we call, in the case of Achronix, RLBs, resource logic blocks, and these are what we call LUTs, lookup tables, that in this case 6 input, and these are arranged in columns, and then there's also memories that are arranged in columns, and then there's a switch box that is responsible for routing signals between the logic elements and the memories, and that is how you program the logic. The designs can be modular, and they can be programmed on the fly, and the design is done using HDL, the HDL Verilog type of languages synthesis. So that is the basic technology. What embedded FPGA technology is taking this and making it a piece of IP that a customer can then integrate with their SoC. So obviously we have to make this available in the same process nodes as the target SoC, so 7 nanometers, 5 nanometers, 16, depending on what the technology the end customer is using. We have it available across multiple process nodes. And what happens is you put this embedded FPGA inside of your SoC, and then you have a high density of wires that are able to connect to it from other subsystems to allow you to then use that as a programmable element within the SoC, and then you basically can put in different lookup tables, memories, and even DSP the machine learning processors. So there's also, let's say, hardened elements that would be available in the column, and these would then be used with the logic to provide some sort of functions in the case of DSP, signal processing, and other functionality like that. In the case of Andy, where they wanted to look at high-speed analog front ends, something like a DSP would be a very valuable piece of IP inside of the core. So how do we configure these embedded FPGAs? This is unfortunately PDF, but if I had a PowerPoint, you'd see little knobs spin, and then different columns would get populated. But you can look at the end results here. And so this is a very large fabric. It's about 1.5 million logic elements, 60 megabits of memory. And you can see here they're organized in these columns, and obviously these switch boxes that I showed you earlier are used to interconnect them across the columns and between the elements inside the column. Now, we've had some discussion today about UCIe. We've had discussions about a bunch of wires. UCIe has support for PCIe and CXL and a streaming raw interface. A bunch of wires has a TLP interface on the rear. But if you're wanting to run, say, AMBA protocols, or if you want to run Ethernet or even some proprietary protocols, there is nothing currently defined in the standards that address that, right? That is the left up to the designer part of the system. So this protocol layer now, if you want to build a chiplet that is, let's say, generally reusable with other chiplets, you want to have some flexibility in that protocol layer. One of the killer apps for embedded FPGAs is putting an eFPGA logic block where the, let's say, die-to-die interface, the transaction layer, or the data link, depending on what you want to call it, terminates, and then you want to implement your protocol logic in that protocol layer. So in the case of, let's say, a complex SoC that has processors and other hardened elements on it, you could put a small embedded FPGA IP in line with the physical layer and the die-to-die adapter to then basically implement a protocol layer that's reprogrammable in the field depending on what the protocol du jour is that you're working with the other side of the thing that's interfacing to you. So the embedded FPGA technology gives you this flexibility to reprogram the device to be protocol agnostic, meaning that it can be doing Ethernet, it can be doing JESD, it can be doing any one of these other streaming protocols, but it can also be doing AXI or AXI streaming, all based upon how you program that embedded FPGA layer. Now, we can take the next level, and I think this is where Fraunhofer is going, is actually building a larger block that is, let's say, what you put inside of an SoC obviously is going to be limited by the area that you have to enable that inside the SoC. But what if you want to build a pure FPGA chiplet that can be used for various different tasks? So now you want to pull that SPI core out of that SoC and implement it as a standalone chiplet, and that chiplet could also have the I/O and memory interfaces on it too. So it can either be a, let's say, pure acceleration block, which is just data in, data out, or it can also have hardened interfaces such as PCIe or some other, or memory interfaces going to it. That becomes a much more complex FPGA chip. Now, so here is an example of a fabric, and what I had showed you earlier, which was this die adapter, this physical layer using the FPGA as a shim to make it protocol agnostic. Here, that protocol logic would exist in a portion of the embedded FPGA logic, and then the remainder of the embedded FPGA logic would be then used for whatever functionality that embedded FPGA is implementing. In the case of a signal processing, let's say you have an analog front end, as Fraunhofer is here, you may want to put different DSP, FIR filters in there, maybe just FFTs, IFFTs, depending on what the use case is that's going to be used for the end system. And by making this embedded FPGA chiplet, you can then reuse it across different packaged end devices for different experiments, reusing the same block, but programming in different manners. So, just in conclusion, embedded FPGA IP provides flexible solutions for chiplet die-to-die protocol adaptation, which is that shim. eFPGA-based chiplets provide a flexible solution for programmable accelerators, and embedded FPGA technology can be used to build FPGA-based accelerator chiplets. And I believe Fraunhofer, you're doing a tape out. I don't know if you want to talk about the test chip you're working on.
Yeah, only a short comment to that. So we are currently working here on a test chip, and we expect that we have the first test chip available end of this year, so that we can show them the combination of this eFPGA together with the bunch of wire UCI interface. Okay, thank you very much.
So let's open it up for any questions.